All right, so which of these has line symmetry? So the A does, which is vertically. The B, you can argue if the top loop is bigger than the bottom loop. Maybe not, but C, yes, horizontally. D, horizontally. E, horizontally. F does not. G does not. H is both horizontal and vertical. I is horizontal, and I guess you can make a case for vertical. J does not. K, horizontal. L is not. M, vertical. N does not. O, you can pretty much go anywhere with, and it'll be have a line of symmetry. P does not. Q does not. R does not. S does not. T, if you go horizontal. U horizontal or vertical. V vertical. W vertical. X has 2. Y horizontal or vertical, and then Z doesn't have any, right? Now, your rotational symmetry, and you can kind of work off of your line symmetry, but A is not going to have any, B is not going to have any, C is not going to have any, D, E, F, G. Now, H will, because it has 2 lines of symmetry, so it will have rotational symmetry 180 degrees. I, the same thing. J, no. K, no. L, M, N. O will have an infinite number of rotational symmetries. P, Q, R, S, T. I mean, we're looking for anything that has... So the funny thing about S is that it does have rotational symmetry of 180 degrees, even though it doesn't have any line symmetry. If you just turn your paper upside down, you'll see that S has rotational symmetry. Right, but T, U, V, W, X, Y, Z is the same way, and we need to back up. N is going to be the same way also. If you turn your paper upside down, you're going to see that those letters have rotational symmetry, even though they don't have any line symmetry. So, anyway, there's your alphabet. All right, let's move on and talk about our next transformation, which is going to be reflections. And so we're talking about that, right? We're not talking about taking a figure and picking up and setting it back down on the other side of a line. We're talking about flipping it over that line to where the image is going to be sort of backwards from the pre-image. Okay, so flipping it over a line, and so that's what we're talking about with reflecting. Now, some definitions for you. A reflection, like I just said, is a transformation that uses a line like a mirror to reflect an image. That line that acts like a mirror is called the line of reflection. And so, depending on your line of reflection, there are rules that will govern some of those lines. Not all. Some of these we can just use some common sense, and some of these, the reflection is a little bit more complicated than what we're going to get into with our conversation today, right? So, and like I said before, reflection is going to be an isometry, just like a translation is. So it's going to maintain length and angle measure. Okay? So, the rules that I was talking about before. If you reflect over the x-axis, the y-axis, the line y equals x, or the line y equals negative x, then there are rules that we can use. We can take each point, so each vertex has at a point, we can take each point and manipulate those points very predictably. So for example, if we're going to reflect over the x-axis, all we have to do is take our point and change the sign on the y-coordinate. That's it. If we reflect over the x-axis, we change y. If we reflect over the y-axis, then we change the x-coordinate. If we reflect over the line y equals x, and we'll remind ourselves what that line looks like, then what we do is we just flip-flop the x and the y coordinates. And if we reflect over the line y equals negative x, and again we'll remind ourselves what that line looks like, then we do everything, right? We switch the x and the y coordinates, and we change their sign. So these rules, which we'll give to you for your quiz, they allow us to be very predictable in our reflections. Okay? Now, those are not the only lines that you can reflect in. You can reflect in other lines. If they're vertical or horizontal lines, the reflection becomes very, very easy. For example, here, we're going to take triangle ABC, And so A is at 1, 3. B is at 5, 2. And C is at 2, 1. And we are going to reflect that over the line y equals 1. Y equals 1 is a horizontal line that goes through 1 on the y-axis. In order to do that, since reflections maintain distance and length and angle measures and all that kind of stuff, all we got to do is count the distance from each point to the line and go the exact same distance on the other side. So for A, it's 2 units away from the line. 1, 2. So then we want to go 2 units in the other direction from the line to get A prime. 1, 2 puts A prime right there. B is 1 unit away, so go 1 unit away in the other direction and you get B prime. C is actually on the line, so its distance is 0. That means C prime is going to be right where C is. And then you've got your reflected triangle. Okay? Now, and it's the same thing if we reflect over a vertical line. So we take that same triangle, A, B, C, A, B, C, and now we want to reflect over the line x equals 3. X equals 3 is a vertical line through 3 on the y-axis. And we're going to do this the same way, right?
It is now 3:15.
And it's because we're going to a vertical or horizontal line that we can just count spaces and do the same thing. So to the line of reflection, A is still 2 units away, even though we're traveling in a horizontal direction. So since A is 2 units away, we go 2 units the other side, and A prime ends up being right there. C is 1 unit away, so go 1 unit on the other side and you get C prime. B is 2 units away, so go on the other side, B prime. And there's your new triangle, which just turns around that line of reflection. Okay? So that's the easiest way to do that if we're reflecting over a vertical or a horizontal line. There's some practice here for you. So go ahead and try to reflect in each of those lines in your notes. And each time you can stop the video, start it back up, and I'll show you what your graph should look like, both with the pre-image and the image in it. So there's the first one, what your graph should look like. If it doesn't, try to figure out why. And if you can't, come in and see me and we'll figure it out. So the next one, go ahead and do that one, and I'll show you this one. And that's what the next one looks like. You're way off the grid here, so you just got to kind of fudge it a little bit the best you can. But it should be somewhere in that vicinity. Okay? All right, and then the third one. Try it, stop the video, start it back up, and see how you did. And there's the third one. Okay, so again, if yours doesn't look like this and you're having a hard time figuring out why, then make sure you come in and get the help that you need. Okay? All right. Now we're going to get into some of those more predictable lines of reflection where we can use the rules, right? So first off here, segment FG has coordinates for its endpoints, -1, 2 for F, and 1, 2 for G. And we want to reflect that in the line y equals x. Now remember, y equals x is a line whose y-intercept is 0, so it starts at the origin and has a slope of 1. So you'd go up 1, right 1, up 1, right 1, and so that line would end up looking something like that. Now, we can't find the distance between the point and the line as easily now because it's not a vertical or a horizontal line. You'd have to end up using distance formula and all that kind of mess, and we don't want to do that. So what we're going to do instead is use our rules. There are some rules that were already developed for us. So those rules were, if we're going to reflect over the y equals x line, then all we have to do is flip-flop the x and the y axis for our points. So that means that f prime is going to be at 2, -1, g prime is going to be at 2, 1. And now we can just go plot those points. 2, -1 puts f prime here, and 2, 1 puts g prime here. And so there's our segment reflected over okay? Which is a little bit odd. It's not exactly what we'd think. It's not like we took this segment and just flipped it over vertically or horizontally. It definitely went at an angle. And so we have to be a little bit careful about just making some assumptions there. Okay? All right, so there you go. The next one is we're going to reflect the exact same segment, but now we're going to do that in the y equals negative x line, right? And so there's the original segment. That's the pre-image. The y equals negative x line has its y-intercept at 0. The slope is negative 1, so you go up 1, left 1, or down 1, right 1. Either way gets you in a line that looks something like that. Now again, we use our rules. F prime. To find f prime when you're reflecting over the y equals negative x line is to switch your x and y axis, switch your x and y coordinates, but also change their sign. So you get negative 2, 1 here, and g prime would put you at negative 2, negative 1. So our new segment would be at negative 2, 1 here is f prime, g prime at negative 2, negative 1, and so that would be your segment. Okay? All right, and then the next two are examples for you to go ahead and graph. So do those. Reflect over the y equals negative x line in this one. And then the y equals x line for the second one. And you can stop the video. I'll do it at the same time. You can start it back up and see how you did. Okay, there you go. The first time you can definitely see the reflection over that y equals negative x line. The second example, it's kind of interesting. You just kind of get the same triangle, right? This must be at the very least an isosceles, if not an equilateral triangle. But when you turn it, when the line of reflection goes through the triangle, through a vertex, and then you just turn it, this guy ends up mapping onto itself. Okay? But that's it. Just using those rules to get there. This next example, in example 3, verify that f prime is perpendicular to y equals negative x. That's not too tough. I mean, the slope here for y equals negative x is negative 1. We know that opposite reciprocal slopes are perpendicular to each other. So all we got to do is come up with the slope for f prime. We need to go back to that example, right, which is right here. So f prime would be that segment right there. So we'd want to use the points. So f is at negative 1, comma 2. F prime is at negative 2, comma 1. So if we find the slope for that, we'd go 2 minus 1 over negative 1 plus 2. That would give us 1 over 1, which is just positive 1. So the slope for f prime is positive 1. These guys are definitely opposite reciprocals, and so therefore those segments are going to be perpendicular. Okay? So there you go. You got homework sitting out in Canvas. Make sure you have that guy done by next class.